This is the fourth video on section 7.4, double integrals with polar coordinates. And so we're going to look at example 217. Example 217 is asking us to calculate the volume of the region that's inside the sphere centered at 0, 0, 0 of radius 9, but outside the cylinder whose base is the circle centered at 0, 0, 0 of radius 3. That's what we're being asked to do. So we want the volume of the region that's inside the sphere but outside the cylinder. It is easier to calculate the volume of the region that's inside of both. So that's what we're going to do. We're going to find the volume of the region that's inside of both and then subtract that from the volume of the sphere. Because we have a formula for the volume of the sphere, it's just 4/3 pi r cubed. So in the end, we'll calculate this volume and then we'll subtract it from the volume of the sphere. Here's the equation of a sphere. We're going to write the top half of the sphere as a function of x and y. So if we simply solve for z, we have z as plus or minus the square root of the quantity 81 minus x squared minus y squared. So we'll let f of xy be the top half of the sphere. So we ignore the negative and we just have 81, the square root of 81 minus x squared minus y squared. So this is our function. So we want to find the volume of this part here. So we'll set R as a set of xy such that x squared plus y squared is less than or equal to 9. So it's just the circle centered at 0, 0 of radius 3 in the xy plane. And then if we integrate over R of our function, that gives us the volume up here. We want the volume of the whole thing, so we multiply by 2. So again, this integral here gives us the volume above the xy plane. But we're going to multiply by 2, so we get the volume of the whole region. We're going to use polar coordinates because our region in the xy plane is a circle, so it's easier to use polar coordinates here. So r ranges from 0 to 3, theta ranges from 0 to 2 pi, and we have our function. So the 81 minus x squared minus y squared, that's just 81 minus r squared. Then we have the r, dr, d theta. So here's our function converted to polar coordinates, r, dr, d theta. This is a fairly straightforward integral with some not so friendly numbers along the way. So we find an antiderivative with respect to r right here. The r limits of integration are 0 and 3. So we substitute 3, substitute 0, subtract. Here we go. And so now we just have a constant. Again, not a very friendly constant, but it's just a constant. We're going to simplify it a little bit. And now we're going to integrate this constant with respect to theta. So it's just that constant times theta. That's the antiderivative. Substitute 2 pi, substitute 0, subtract. This is our integral. But remember, the integral doesn't directly answer the question that we're being asked. What we've done with this number here represents the volume that's inside both the sphere and the cylinder. It's not what we want. We want the volume of the region that's inside the sphere but outside the cylinder. So we take the volume of our sphere, 4/3 pi r cubed, right here, and subtract the volume that we just calculated. So we take the volume of the sphere, subtract the volume of the region we just calculated, and that simplifies to this.